Hi everyone, today I'm going to be talking about non-steady state slip rates emerging at restraining bends under constant remote loading. This is work that I'm doing with Michele Cooke at the University of Massachusetts in Amherst. Slip rates are inputs for seismic hazard assessment, but assuming that long-term slip rates derived from the geologic record can predict future seismic hazard, we're presuming that long-term slip rates are constant. When we look at 10 recent paleoseismic and tectonic geomorphologic studies from all over the globe and of different fault types, we see that each fault type in different localities exhibit slip rate variability. And slip rate variability is defined quantitatively in Cowie et al. 2012 using some standard deviation of the slip rate for a window divided by the long-term slip rate. And in this case, we use a window with the length of 5 times the recurrence interval to exclude any aleatoric variations caused from the earthquake cycle. On the right, we show the slip rate variabilities for the 10 recent studies, and we show that there's not a correlation between the type of fault or the long-term slip rate and the slip rate variability. This does lead to the question, however, of what is causing slip rate variability over periods of time longer than earthquake cycles and shorter than millions of years. For this talk, I'm primarily going to focus on fault interaction and more specifically fault reorganization, which we define as the abandonment or growth of fault segments. In order to investigate how fault reorganization impacts fault slip rates, we're going to use scaled physical experiment results, which allow us to directly observe and record the slip rate history along every point at the fault, as opposed to the geologic record that may only capture snapshots in time of the deformation record. We use wet kaolin clay in our experiments, and this is a biviscous material, meaning it has an elastic and a viscous component. The reason we use wet kaolin clay as opposed to dry sand is for the clay's higher cohesion, which allows for the growth and reactivation of sharp faults. As you can see on the right, sometimes even slickened lines are preserved on the fault surface. To scale the length of this material to the crust, we can adjust the shear strength by adjusting the water content and using the Moore failure criterion. And so what we get is that with a shear strength of about 90 to 110 pascals of the clay, we get 1 centimeter of clay is 1 to 2 kilometers in the crust. Similarly, for the time scaling, we can use the viscous relaxation component in the clay and scale that to the viscous relaxation in the crust, and get that 1 minute in our experiment is equal to about 2 to 20,000 years in the crust. In all of our experiments, we use a tabletop split box apparatus. So one side of the box is fixed while the other is driven by stepper motors, which we control with the computer. Within this box, we fill it with a clay pack and then pre-cut a vertical fault to match the basal plate discontinuity geometry. And this is just for reliability purposes and matches the figure on the right. And then we sieve some sand onto the surface of the clay to be used as passive trackers or tracers in digital image correlation that allows us to extract the incremental horizontal displacement field and from that get at the slip rates at every point along faults and incremental strain rates. And then on the right, I just want to point out that the red dashed box showing the region of interest, or ROI, is designated such that we exclude boundary effects within our experiments. In this animation, we can see the incremental horizontal strain, and the color is denoting the type of strain, while the magnitude is denoted by the opacity. So first we see the pre-cut fault is slipping, and then a first new fault propagates from the left kink, accommodating both dextral shear and contraction. And as this segment is abandoned, we see the growth of a second new fault in the top of the frame that also accommodates dextral shear and contraction. We will revisit this faulting history as we take a look at the slip rate history. In order to determine which sites are representative or which histories are distinct, we plot the slip rate at every point on the faults throughout the experiment, which are shown in gray, and then we calculate the probability density functions every 20 millimeters of displacement to reveal that there are actually 6 distinct slip histories, and those are shown in color. What we then notice is that these 6 distinct slip histories map well onto 7 segments. And the reason for 7 segments instead of 6 is that the portions of the fault that are parallel to the remote loading actually make up the 2 end segments in this experiment. What we do with this information is take 6 representative sites for each of these distinct slip histories and monitor the slip rate history throughout the experiment. If we watch animations of the incremental strain and the slip rate with time, what we find is that as the first fault grows, we see a general increase in slip rates through the restraining bend, and as this fault dies, we see a decrease in slip rates, and as the second new fault grows, we see a combination of increasing and decreasing slip rates at different sites. In this animation, the sites are advecting with the material. I will now focus on 3 periods of slip rate variation and discuss what is happening with the fault system and how it's reorganizing during these times. This first period of slip rate variation occurs over a time period that scales to 46 to 460,000 years in the crust. If we look at Site E, which is the site on the first new fault, we can see that as the slip rate through Site E increases, there are also changes to the slip rate at sites C, D, and B. During this time period, Site C exhibits an increase in slip rate. Sites D and B also exhibit an increase in slip rate, but not as much as Site C. Site C is in the middle of the pre-cut restraining bend segment, and what may be occurring is that as the first new fault propagates and accommodates both dextral shear and contraction, it may be effectively unclamping the kinked portion of the pre-cut fault. And I will definitely get back to what I mean by clamping and unclamping in a few slides. Moving on to the next period of slip rate variation, we see that the segment through Site E has now been abandoned, and we also see a decrease in the slip rate through Site C, which is on the pre-cut restraining bend. This decrease happens over a period of time that scales to 30 to 300,000 years in the crust, and also corresponds to a period before the second new fault is active. The third period I want to talk about is when the second fault is active, and specifically when the slip rate at Site F is increasing. What we see is that generally Site C decreases over this time period that scales to 140 to 1,400,000 years in the crust, while Site D is increasing. If we compare the location of these two sites, Site C is in the middle of the pre-cut restraining segment, while Site D is on the outside of the linkage point for the second new fault. What may be occurring is that Site C could be experiencing effective clamping, and Site D may be benefiting from being outside of that linkage point, and the slip on the new fault and the pre-cut segment are being transitioned to that site or through the fault at that site. We can also talk about Site B, which is exhibiting a large decrease in slip rate, and at the blue star, we see that this site transitions from being outside of the restraining bend or on the outside of that first fault linkage point to inside the restraining segment. This may explain the large decrease in slip rate that we see over this time period. I now want to talk more about this clamping and unclamping that I've mentioned, and I want to talk about it in the context of what might happen to the strike slip rates as convergence is accommodated on fault versus distributed off of faults. If we look at the stacked convergence maps for 2 different periods, we see that prior to any new fault growth, the convergence is accommodated in a diffuse manner, whereas once we get this first new fault to grow, convergence is accommodated on fault. What this does to the kinked portion of the system is effectively unclamps it as there's extension in the hanging wall of this reverse fault that's growing. If we then think about how this affects the strike slip rates, as the restraining segment or the kinked segment of the pre-cut fault is unclamped, there is more dextral shear strain accommodated on this pre-cut segment as there is less normal force clamping this segment. We can now start to draw some conclusions from our experimental results. We noticed that these large slip rate variations, like the 3 periods I discussed, correspond to periods of fault reorganization, and they also happen over time periods that scale to 30,000 to 1,400,000 years in the crust. But there are also smaller variations that occur at time periods that do not correspond to these large periods of fault reorganization, like fault growth and abandonment. We can also compare a few of our site slip rate variabilities that we calculate to the 10 studies that we talked about at the beginning of this talk to see that our site slip rate variabilities fall within the range of the crustal values from the 10 studies. From this experiment of a 15-degree restraining bend with a 2 centimeter step over, we see that sites within the restraining bend have the largest slip rate variations and the largest slip rate variability values, as we show on the right, and that the greatest changes in slip rate correspond to periods of fault reorganization. Additionally, the main point that we want to make is that slip rates can change under constant remote loading, and the results of this study show the potential for the emergence of non-steady state slip rates within restraining bends, even under constant remote loading. Thank you.